Hi, everyone. Welcome back to a podcast here for Managerial Economics. This is lecture 4A about production. And so for the very first thing that we talk about is the role of the firm. We know that firms use productive resources. These are just inputs or factors of production, however you want to call them, to produce goods and services, which ultimately satisfy some sort of unlimited wants that consumers have. And so we began this chapter by splitting up our inputs into non-human versus human inputs, so that our non-human inputs essentially are land and capital, whereas our human inputs are labor and entrepreneurial ability. So as we dive a little bit deeper into these non-human resources, we say that land specifically we think of as gifts of nature. These are raw materials that we find in the earth or we're able to use in terms of production. Whereas capital, we want to make sure that we understand that capital is describing the non-financial kind. These are tools, machines, equipment, office buildings, anything that goes into the production process for a firm. And then when we talk about labor, we discussed a little bit about these are the physical and mental talents of individuals engaged in the production process. We usually like to say that it's fairly unique to production and that the intensity of labor services essentially decides for itself how much to use. We didn't go very in depth into this idea, but we did end up talking about essentially differences here, being things like low-skilled labor and high-skilled labor. And it was important for us to make this distinction between the two. This is going to come up later on as we look a little bit more into the substitutability of inputs. And then we think of entrepreneurial ability as this last input. And we want to believe that this is the person who essentially facilitates the renting of land, labor, and capital. They're the ones that make non-routine decisions. They're the innovators of some product or some process. They're the ones that are creating, refining production techniques. And so this is very different from that low-skilled or high-skilled labor in that this person is the intermediary. So as we move on, then we talked a little bit about the organizational structure of the firm and what that means for us. And so we assume right now that firms are maximizing profits. And so to some degree, this needs to put in place this idea of maximizing profits so that entrepreneurs have some incentive to take risks and to participate in commercial activities in some way. Without it, with no incentive, we would not necessarily have people stepping up to facilitate these products. And so the incentive is important. So essentially, the right mix of goods and services are produced for a market. And it can be shown when the profit motivation is diluted in some way, less goods and services are produced. And that should intuitively make sense. If there's no reward, why go through the effort? So we then moved on to specifically the production function, we called it. And this production function for us is a technological relationship that describes the process whereby factors of production are efficiently transformed into goods and services. And so we have a very general production function. We write it like Q is equal to F of K, L, and M, where K, L, and M are capital, labor, and land, respectively. So what else do we know about the production function? We assume that firms in a competitive environment will strive for producing essentially at the lowest cost possible. This is efficient or cost efficient. And we'll talk more about this later. We also like to believe that in a free market economy, there's a tendency for more efficient operations to drive less efficient firms out of an industry. Let's further assume that we can simplify our inputs even further so that we're just concerned essentially with choosing labor or capital. So once we do that, we also assume that labor and capital can be substituted for one another. This depends heavily, essentially, on the degree of substitutability, as well as the rental price of capital and wage. And those two terms, the rental price of capital and the wage for labor, are going to be very important later on. Firms, essentially, which are striving for profit maximization, will also strive for producing goods in the least costly way, essentially minimizing the total cost. So, equivalently, a firm that operates efficiently will choose that combination of productive inputs that will maximize production subject to a given operating budget. So the production function defines essentially for us this maximum output obtainable from a particular combination of inputs. So it's clear that later on, input prices must be combined with the production function determines which of the many, many possible combinations of inputs are most desirable for a firm, given that they want to profit maximize. So one of the very first production functions that we will generally see for now is the Cobb-Douglas production function. It's it's highly specialized and generally unique to individual firms. So generally at best, we can approximate the relationship of inputs to outputs. And more often than not, the Cobb-Douglas production function does a fairly good job of this. And so we like to think that this output is now dependent on a few different inputs. So we have the input A, which essentially for us is going to be we're going to eventually call it technology. We have K as our capital and L as our labor, but then we have these parameters alpha and beta, which are going to become very important for us later on down the road. We're going to understand essentially what they mean in the next set of slides. So as we continue here with our production function, we find that there's three essentially properties that fall out of the Cobb-Douglas production function. The first is understanding that there's some substitutability between capital and labor. The second is the idea of there's some returns to scale. And third, we have this law of diminishing marginal product occurring. So what we have here, suppose that we have this Cobb-Douglas production function where we have A, our technology is 25, K and L are both to the 1/2. So if we were to ask ourselves what combination of inputs, up to 8 inputs each, get us 122 units of output Q. If we were to essentially just talk about whole numbers, we would only have about 4 choices. But what we find out here is that if our inputs are divisible, we essentially have an infinite number of choices to pick from. And so what we get here, if I draw this, and I draw this poorly here, is we have a production hill, if you think about it. And this hill essentially looks like this. And so what we could do is come from a variety of different ways to come up this hill. And so what we want to be able to do is essentially understand, so if this is Q and these are inputs L and K, what we want to do is essentially get up this hill as high as we can. And that would be maximizing total output. But we're going to be constrained in some way by some relationship between L and K. So as we then move on, we talk a little bit more about each one of these characteristics of the Cobb-Douglas production function. The first, again, being substitutability. And this is, again, the very first idea we discussed in any type of constrained optimization, is that there's going to be some sort of ability for capital and labor to be interchanged with one another. Again, if we were only held to integer amounts, if we weren't held, there are literally infinite amount of solutions. And so we understand that managers are going to be faced with very specific input constraints, whether that be prices of capital and labor, or it might be the quantity of capital and labor available. So we're going to take a look more about this later on. But we spent a lot of time looking at returns to scale. And so we defined 3 different returns to scale properties. And that is constant returns to scale, increasing returns to scale, and decreasing returns to scale. So the very first, this constant returns to scale, tells us something very important. And so we essentially started out like this. We said that Q is equal to K to the alpha, L to the beta. And if that's true, then we can do this. We can say, let's scale our inputs by some Z. So all we know is Z is greater than 0. And if that's true, we want to know what happens here. If we have KZ to the alpha, LZ to the beta. There we go, LZ to the beta. We want to know what happens to the Q on this side. So if we have ZQ is equal to Z alpha plus beta, K to the alpha, L to the beta. And so we were able to distribute each exponent, alpha and beta, to both Z and K, and then again Z and L. And then we were able to collect like terms with Z. So we were able to collect the exponents of alpha and beta. Now this is going to tell us something because we know originally, so from the original Cobb-Douglas function, Q is equal to K to the alpha, L to the beta, so that we have ZQ is equal to Z to the alpha plus beta times Q. So when we go back to the slides, we realize that if alpha plus beta is equal to 1, then that means we scale our inputs by Z, and we also scale our output by the same amount. So if we were to essentially double, if Z were equal to 2, we would say that we could go from K equals L equals 1 to K equals L equals 2. Right? So ZK, ZL is equal to 2, so that ZQ would have to double. And that would be constant returns to scale. If it was less than double, then we would have decreasing returns to scale. And if it was increasing, if it increased more than double, then we would have increasing returns to scale. So how do we know that's true? Well, we look at alpha and beta. If alpha and beta are equal to 1, we have constant returns to scale. If alpha and beta are greater than 1, we have increasing returns to scale. And if alpha and beta are less than 1, we have decreasing returns to scale. But as we saw in the homework, that's not the only way that we can achieve this problem. We can actually put numbers into our production function to determine whether or not we have increasing, decreasing, or constant returns to scale. So what other idea came from the Cobb-Douglas production function is one that's very important to us, and that's the law of diminishing marginal product. So what we say is when at least one productive input is held fixed, while at least one other productive resource is increasing, output will also increase, but be successfully smaller increments in its increasing. And so we have to be conscious of this fact. This is, when we talk about this in class, this essentially, this idea of diminishing marginal product is the idea of there's too many cooks in the kitchen. So we want to know what happens to total product or our production function with that occurring. So as we move on, we first want to decide, and so our law of diminishing marginal returns is going to play a really important role a little bit later on, but first we need to define our short versus long run production schemes. So that when we talk about the short run, we have to say that a firm is observing some sort of fixed factor. Whether that be capital or labor, something has to be held fixed or constant. And if we kind of position this ourselves as producers in some way, We found that maybe like a lease to an apartment would be a fixed factor. Maybe your insurance is a fixed factor. For a firm, you would also have leases and insurances. You would also have specific limited number of capital inputs like ovens or machines. And so to contrast that, we look at the long run, and the long run becomes a period of time where all factors of production can be variable. So given that statement, let's look at some short run analysis. And so let's look at output, the total product of labor. So let's say that capital is fixed for us right now. So we have K sub naught. And so that's going to be some number for us. And so we find out in this instance that we can now determine when K is fixed, how much is contributing to output when we change labor. So that's the total product of labor here. And so our average product of labor then, simply for us, is the total product per unit of labor usage. So we're just going to take that production function with capital being fixed and divide it through by L. That's our average product of labor. So then how do we get our marginal product of labor? Right, our marginal product of labor is then defined as the incremental change in output associated with an incremental change in any labor usage. So for us, this is just going to be the first partial derivative of our total product of labor with respect to labor. So we can write this notationally a few different ways. We can talk about the marginal product of labor is equal to the partial of total product of labor divided by labor, which is equal to the partial of Q sub L over the partial L, which is equal to the partial of the functional form of fixed capital and labor divided by the partial of L. And we can do the same analysis if we wanted to, essentially for capital. So we had a problem here. Suppose that you're given the following production function. Determine the marginal product of capital and the marginal product of labor when K is equal to 25 and L is equal to 100. So in this instance, what we want to do for this problem is we realize that we have Q is equal to 100, K to the 0.6, L to the 0.4. So let's fix capital so that we're looking at total product of labor is equal to 100, K sub naught 0.6, L to the 0.4, so that we take the partial with respect to labor, so that we have 40, K sub naught 0.6, L to the negative 0.6. So we can simplify this just a little bit so that we have 40, K sub naught over L all to the 0.6. And now we can plug in our values. So we can plug in our values so that we get 40 times 25 over 100. So we get up to the 0.6. So if we were to solve for this, we should be able to get 17.41. And if we were to continue, now saying our total product of capital is equal to 100 K to the 0.6, L sub naught to the 0.4, so that we have our first derivative with respect to capital. So we have 60 times K to the 0.4, negative 0.4, L sub naught to the 0.4. So we can simplify this. So we have 60 L sub naught over K to the 0.4. So we have 60, 100 over 4 to the 0.4. And then when we solve for this, we should get